Welcome to qnawire.
Okay, let's go ahead and start this problem. We are given a three-part question, but the answers for part B and part C, I usually always do it anyways. It's basically the parametrization of the curve or the surface and the visualization, graphing it, so that whenever you solve these kind of problems, it's just easier to see what's happening visually in order to make sure that the dot product is taken properly, the cross product is facing the right direction, etc. So we're just going to go through it exactly the same way that we have been doing it. So f is given as x squared z comma xy squared comma z squared, and the curve c is given by the plane x plus y plus z equals to 1 and intersecting with the cylinder x squared plus y squared is equal to 9. So because it asks us to do the visualization, I want to go through that a little bit first. So if you imagine that x squared plus y squared is equal to 9 is this cylinder that looks like this, we know that the radius is equal to 3. And right here, the center passes through the z-axis. We have a plane x plus y plus z is equal to 1. And graphing that one is quite simple if it's on the first octant. It just passes through 1 comma 1 comma 1 like this. And I want you to remember that this triangular sheet, it actually extends forever. So it's more like a sheet that aligns with this triangle like this. Okay, so hopefully that will help you visualize this thing a little bit more. So when I draw that sheet of paper so that it cuts through the cone, it will look something like this. And that's basically what I drew over here. Okay, so let me get rid of those. All right. Now the parametrization. Using a cylindrical coordinate system would really be helpful here. So I can say that x is equal to r cosine theta, y equals to r sine theta, z is equal to z, but I want it in terms of r and sine theta. And because we know that the plane is 1 minus x plus y, let's write it as 1 minus r times cosine theta plus sine theta. And of course, you don't have to write it exactly the way I did. I just like to write it this way more. Okay? All right, so we're done with the parametrization portion and the graphing portion. So let's move on to the evaluation. Okay? All right, as usual, we are asked to evaluate the line integral f dot dr. By using Stokes theorem, we can evaluate it using the surface by taking the dot product of the curl of f with the normal ds. Okay, so we can calculate the curl first. Again, it's a quite straightforward calculation, so I'm not going to go through into detail, but I've already done the calculation. It turns out to be pretty nice. It's 0 comma x squared y squared. I'll put this in terms of r and theta later. Okay, the normal vector is very simple here because we are already given the plane, the equation of the plane. So it is going to be parallel to 1 comma 1 comma 1. So the dot product is going to be very simple here. curl of f dot n will simply be the sum of x squared and y squared. So what we're going to evaluate is the double integral through s of x squared plus y squared. Now, I want to evaluate this double integral using the cylindrical coordinate system. So I will get the double integral. X is r cosine theta, y is equal to r sine theta. A z doesn't show up, so that's good on our end. X squared plus y squared is, of course, just simply r squared. And then we changed our coordinates from x, y into r and theta, so we will have r dr d theta. So the radius changes from 0 to 3, because as you can see, the projection of this surface onto the xy plane is simply the circle here. Okay, it's also given in this equation right there. And because it's one revolution, the angle changes from 0 to 2 pi. So long story short, we're evaluating the double integral of the angle changes from 0 to 2 pi, the radius changes from 0 to 3 of r cubed dr d theta. So it'll simply be 2 pi times 3 to the 4th power divided by 4, and that simplifies to 81 pi divided by 2. And that answers all of the question of this problem.